Step 1 is to state the problem. How many of these molecules are polar? You must draw the Lewis structures for each molecule and find their partial charges, bond dipoles, and the molecular dipole. The molecules are SO3, OF2, BeCl2, CCl4, and O3. The next step is to give an overview or the big picture. First, we're going to draw the Lewis structure, identify the bond dipoles using differences in electronegativity values of the atoms, identify net molecular dipoles based on molecular geometries, and think about the molecular geometry in order to finish solving the problem to decide whether the molecule is nonpolar or polar. Solve the problem, and we will go through each molecule one by one. If you are lazy when you make the Lewis structure and throw dots on the structure, you will get them wrong. So first we will start with SO3. So first you have to find the total amount of valence electrons in this molecule. So there's 24 valence electrons because there's 6 valence electrons in S and 18 in the O3 to get 24 valence electrons. So we begin by placing electrons on the outside atoms first, starting with octets on the outside atoms. So we're going to draw the S in the middle, O here, O here, O here. And just looking at this molecule, we know that there's going to be a violation of the octet rule for S because it's in the third row or below in the periodic table. And so we're going to start by drawing electrons on the O to give it an octet of 8. And since there's 24 electrons, I know that I have to be careful with where I place the other electrons. So I'm going to give this a double bond here, this here, this here. So the S is going to have 12 electrons, 2, 4, 6, 8, 10, 12. The O will have octets, so 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 to give a total valence electrons of 24. So 1 octet, 2 octets, 3 octets. S does not have an octet. It's a violation of the octet, but we have already used 24 valence electrons. We must make each O have a double bond to the S, so each O and S can obtain an octet. Now we have to find how many electrons are left over. So the S makes an octet rule due to the 3 bonds made between the S and O. So we made use of all the 24 valence electrons, which is good. So now let's think about the bond dipoles. The highest electronegative atom, O, will have a partial negative charge. And the S will have a partial positive charge. And the bond dipole's positive tail on the S and its negative arrowhead will point toward the O on the most electronegative atom. And we will have to make that for every atom as well. Another bond dipole going the other way and another pointing down. So we have 3 bond dipoles. The bond dipole arrow shows you the direction of the charge separation, and the length of the arrow represents the magnitude of the charge separation. In order to determine whether the dipoles cancel or not, you have to think of the molecular geometry. If the molecule is linear, these 2 bond dipoles will cancel. We have to think about the molecular geometry. This molecule has 3 domains about the center atom, 1, 2, 3. This molecule has 3 domains, so the molecular geometry will be trigonal planar. Because it has 3 domains and 0 non-bonding pairs. So now we're going to draw the molecular geometry. The S will be in the middle and an O coming from the top and 2 diagonal coming down, looking like this. And then we can also draw the bond dipoles here as well. The molecule is not linear, it is trigonal planar. Now we will draw the molecular geometry structure shown here. There are 3 domains and no non-bonding pairs. If you look at the bond dipoles, they look like this is one here, and one here. The only way the bond dipoles cancel in this electron domain geometry is if all 3 domains are the same, and they are all the same. So the dipoles are able to cancel. So there's a 0 net dipole, meaning that this molecule is nonpolar, meaning there's no net dipole, and when we cancel the dipoles in this bond, So this molecule is nonpolar. So the next structure that we're going to look at is the OF2 structure. So let's check the Lewis structure. So one of the things that I always do before leaving my Lewis structure is to make sure that each atom has an octet. And I have accounted for all the valence electrons in the structure. There are 2, 4, 6, 8 electrons on the F, so it's an octet. 8 electrons on the oxygen, 2, 4, 6, 8, so it has an octet as well. And 8 electrons on the other F, 2, 4, 6, 8, so that also has an octet. Let's make sure that there's a total number of 20 valence electrons. I will count by pairs, then multiply by 2. So 1 pair, 2 pair, 3, 4, 5, 6, 7, 8, 9, 10 times 2 gives you 20 valence electrons. So this structure should be correct. Step 2 is to find the bond dipoles. I have to first find where the partial charges are. I have to identify the atom with the highest electronegativity. That would be the fluorine, and I will label these with partial negative and partial positive charge on the oxygen. So the oxygen will have a partial positive charge, and the fluorines will have partial negatives because fluorine has a greater electronegativity than the oxygen. The F's are negatively charged while the O is positively charged. The bond dipoles will look like this. Positive dipole on the O going toward the negative on the F, and positive O headed out toward the negative on the F. Now to step 3, use the molecular geometries to find out how the dipoles add. This is a bent molecular geometry because there are 2 bonding domains and 2 non-bonding domains. It is bent because the domain geometry is tetrahedral due to the 4 domains here, and the molecular geometry is bent because there are 4 domains, 2 of which are lone pairs. The dipoles go from the O to the F, because of the molecular geometry. The net dipole will be out in this direction, going downward. This is the molecular geometry. So the net molecular geometry will be going downwards. The dipoles in the bonds do not cancel because of the molecular geometry being bent. There is a net dipole, and this molecule is polar. The next structure we will look at is BeCl2. Look at the electrons on the Cl atom, and Cl atom has its octet, 2, 4, 6, 8, 2, 4, 6, 8. The Be atom only has 4 atoms, so it violates the octet, 2, 4. But we know that it is allowed. But we know that it is an allowed octet violator. Let's check that we used exactly 16 valence electrons. We will count by pairs and then multiply by 2. 1 pair, 2 pair, 3, 4, 5, 6, 7, 8. So 8 times 2 is 16 valence electrons. Let's go to step 2 and think about the partial charges. We identify the high electronegativity atoms. They would be the Cl atoms in this case, so they would get a partial negative charge. And the Be is the least electronegative, so it would get a partial positive charge. Let's think about the bond dipoles. There will be one dipole moving from the Be moving out to the Cl, and there will be another from the Be to the Cl. Now we move to step 3. We have to think about how these dipoles add together, but to do that we have to know the geometry of the molecule. I have redrawn the molecular geometry here as a linear molecule. All of the bond angles are 180 degrees apart, and this is has linear molecular geometry because there are 2 bonding domains and 0 non-bonding pairs. So the 2 dipoles in this case will cancel when added together. So you have the dipole here, and they will cancel because the domains are the same. So let's look. Domain 1 is a single bond to Cl, and domain 2 is a single bond to Cl. Because both domains are the same, the bond dipoles are going to cancel and there is no net dipole. This is a nonpolar atom. Next, we will look at the Lewis structure for CCl4. There are octets on all the outside Cl atoms, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. There Let's check to make sure that we use the exact amount of correct valence electrons, which would be 32 in this case. So yes, we have used the exact amount of valence electrons because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs times 2 would give you 32 valence electrons. And the most electronegative atom is chlorine, so we would allot the chlorine's partial negative charges. And the carbon a partial positive charge. So the most electronegative atom is chlorine, so all the chlorines will have partial negative charges, and the dipole will go from the center of the C to the Cl's. Be careful, I said dipole, but not what kind. We are talking about bond dipoles, the bond that exists between two atoms. To find the molecular dipole, I have to think about the molecular geometry, which is what I've drawn here. This molecule is not a planar molecule with all of the atoms in a plane. It is arranged as a tetrahedral molecule, meaning that there are 4 domains. I will redraw the molecular geometry to simulate a 3D tetrahedral geometry. The rule about tetrahedral geometry is that the only way the bond dipoles cancel is that if all 4 domains are the same, which they are, and this makes this molecule a nonpolar molecule. It's nonpolar because there are 4 domains and all domains are exactly the same. So the dipoles in the bonds of the first structure will cancel, which gives a nonpolar molecule. And I can draw the dipoles here as well to show that they cancel because they're all the same. And this molecule is nonpolar. Next, we will look at the Lewis structure for O3, or what you can call the ozone structure. One of the things that I always do before leaving my Lewis structure is to make sure that each has an octet, and I've accounted for all of the valence electrons in the structure. There are 2, 4, 6, 8 molecules on the O to give an octet, 2, 4, 6, 8 here, 2, 4, 6, 8 here. So, one being from a lone pair in the middle, and then a single bond here, and then a double bond here. Let's make sure that there's a total of 18 valence electrons. So I will count the pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs times 2 would give you 18 valence electrons. So this structure should be correct. Step 2 is to find the bond dipoles. No bond dipoles are needed to be drawn since each atom is the same, being oxygen, and they all have the same electronegativity. The domain geometry is trigonal planar because you have 3 domains, 1, 2, 3. So molecular is trigonal planar. I'm sorry, the domain geometry is trigonal planar. And the molecular geometry is bent. Trigonal because you have 3 domains, 1, 2, 3 for domain, and then molecular being bent because you have 2 bonding and 1 non-bonding pair. Are you curious as to why I have seemed to ignore the fact that there is a double bond on the right, and a single bond on the left? These 2 domains appear not to be the same, but in fact they are the same. This molecule has resonance as shown in 2 structures here. You can either have a double bond on the right or a double bond on the left. So the actual molecule will be a hybrid of these 2 structures as noted by the dotted line. The actual molecule will have 1 1/2 molecule on each side, but both of these bonds will be identical. Both of the 2 bonds are identical. 1 domain here and these 2 domains are equal. But these 2 are equal, but the third is not because it's a non-bonding pair. So because we have 3 domains and one is different, the molecule is polar. So now we're in a position to answer the question that we were given. So this is polar. So now we go back to the original question, and it says, how many of these molecules are polar? So we're in the position to answer this. So can you guess which ones are polar? It's OF, 2, and O3. SO3 is nonpolar because all three domains were the same when they were added, so they canceled. OF2 is polar because we found that all of the domains in this molecule are not the same because of the two non-bonding domains. BeCl2 is nonpolar because both domains were the same and canceled each other to leave a net dipole of 0. CCl4 is nonpolar as well because all four domains are the same and the net dipole is 0. O3 is a polar molecule because the molecular geometry is bent, having two bonds in one non-bonding domain, which makes the three domains different, resulting in a polar molecule. The way we solved this was to think about the Lewis structures, then the bond dipoles, then the molecular geometry to see how those bond dipoles would add together or cancel. Now we will discuss the possible mistakes that one could have made when solving this problem. Every molecule we looked at in this case, or most of them, had fluorines as the outside atom. We put partial charges on those outside atoms, but that doesn't necessarily mean that the largest bond dipole will have a fluorine atom in it. There are the electronegativities of the atoms. A large charge separation is a large difference in electronegativity between the two atoms in the bond. When you look at the difference of electronegativities, when you look at the molecule here, FF, the charge is the difference in electronegativity is 0 because they are the same molecules. Even though this molecule has an O and an F, the charge separation is not that large because the difference in electronegativity is small. O and F have relatively same electronegativities, being 3.5 and 4. And here, this is not an F, and there's a big difference in electronegativity. This difference is 1.4 because you have 3.5 and 2.1 here. It is the difference in electronegativity that makes the largest separation. So a common mistake is thinking that F would be the largest electronegativity, and also you have to make sure of where you point your dipoles. That the head of the arrow has to be towards the molecule that has the greatest electronegativity. So some people might get that confused. And another common mistake is misplacing the dots on the Lewis structures and not making the appropriate single bonds, double bonds, or triple bonds. So it could be in the dipole, the Lewis structure, or electronegativity.